So under synchronization, the second type of problem is the dining philosophers problem. The first one was producer-consumer problem. Now in the dining philosopher problem involves allocation of limited resources to a group of processes in a deadlock-free and starvation-free manner. So what is the problem statement? The problem statement says that there are 5 philosophers and around a table in which there are 5 chopsticks or forks kept beside them and a bowl of rice in the center. So how many philosophers are there? 5. And how many chopsticks are there? 5. So that means it is a limited resource because when you want to eat, you need 2 chopsticks but only, so total you need how many chopsticks? You need 10 chopsticks total. But how many are provided? Only 5 of them are provided. That means the resource is limited. When a philosopher wants to eat, he uses 2 chopsticks, one from the left and the other from the right. When a philosopher wants to think, he keeps down both the chopsticks at the original position. So when philosopher is eating, what he will do? Pick up one from the left, one from the right chopsticks. When he wants to think, he will keep both the chopsticks down. So this is the dining philosopher problem. One simple solution is to represent each chopsticks with a semaphore. When a philosopher wants to grab the chopstick, that means now the philosopher is using the chopsticks. When you want to use the chopstick, you will perform the weight operation, thereby decrementing the value of the chopstick because the chopstick is being used. So perform the weight operation on that semaphore and releases the chopstick by executing the signal operation. So when it is releasing the chopstick, the number is increasing, so you will perform a signal operation. Thus the shared data are semaphore fork is 5. That means there are 5 chopsticks. Okay. Now where all the elements of the chopsticks are initialized to 1. So why are they initialized to 1? That means the first chopstick will be the P1 chopstick. So they are initialized to the 1. Now dining philosopher's problem states that if the semaphore fork is 5 is 1, what will you do? If the condition is true, first thing, that means the philosopher is thinking. When the philosopher is thinking, what happens? Chopstick will be kept down. Chopstick kept down. Now the philosopher performs the weight operation. Once you perform the weight operation, the value is decremented because the philosopher wants to use a chopstick. Suppose the philosopher wants to use chopstick number 1 and chopstick number 2. I plus 1 is 1 plus 1, that is 2. Then the second will use, so first will use 1, 2, then 3, 3 plus 1, 4, then 4, 4 plus 1, 5, then 5, 5 plus 1, 6. Now but we don't have 6 chopsticks. So we write mod of 5. When we say mod of 5, 5 plus 1 is 6. 6 mod 5 will be 5. 6. 5 ones are 5. Remainder is 1. So again over here the first chopstick will come. So we always perform a mod operation with the second weight. So weight fork 1, fork I, that is 1. Weight of fork I plus 1 mod of 5. What it will do? It will now eat because now it has grabbed 2 chopsticks. The philosopher will eat. Once the philosopher has eaten, it will again place the chopsticks again. Fork, signal fork I plus 1 mod 5 and signal fork I. So first it will place the first chopstick, then it will place the 5th chopstick. First it will place the second chopstick, then first, 4th, then 3rd, 5th, then 4th, 1st, then 5th. So it will be placing the chopsticks. When it places the chopsticks, by the signal operation, the value will be incremented. So, but what is